Hi everyone, I'm Dr. Surjit Singh. In this video on Python by examples, we shall write the Python program for the numerical problem that we had introduced in the previous video. Let us begin. In this session, we will write the Python program for the number problem that we explained in the previous video. Find the smallest number of which when digit at units place is shifted to its beginning, that is the extreme left. The new number is 1¼ times the original number. Note that the number of digits are equal in both the original and the new numbers, and the digit transferred is not 0. We had formulated the problem in the previous video and obtained its numerical solution. Now we will write the Python program for this problem. During the solution of the problem, we derived the relations that are reproduced here. Old number is 10a plus d. New number is obtained by shifting the digit at the units place to extreme left. It becomes 10 to power n minus 1 times d plus a. Using the given relation between old and new numbers in the problem, we obtain these relations. Instead of 5 and 4, we will use constants old times and new times in the program. This way, we will be handling all other similar problems. We will have to make corresponding changes in the subsequent expressions to find the values of d and a. We now proceed with the program development. In order to generalize the program, we use variables old times for 5 and new times for 4. However, for illustration, we will still use these values. 46 is saved as denorm. General relation for denorm is 10 into old times minus new times. The end digit is 5, which is the digit following the series of 9s. We calculate its value as 10 minus old times. D is a single digit factor of denorm. To find its valid values, we iterate D from 1 to 9. We continue with the D values only if denorm is divisible by it. If D is not a factor of denorm, we move on to the next iteration of D. For denorm is equal to 46, the only single digit factors are 1 and 2. Den is the quotient when denorm is divided by D. For D equal to 1, den equals 46. Den is used as the denominator in the expression for A. It is clear that the numerator in this expression is not divisible by 46, so this will not yield a solution. Therefore, we proceed to the next value of D. When D is 2, den is 23. We can now determine the minimum number of 9s needed in the numerator in the expression for A to be divisible by den. Let us now see how does the program proceed. To begin with, D is 1 and den is 46. We define n to be starting digit of the numerator. I represents the number of 9s that appear between the initial digit 3 and the end digit 5. The maximum number of 9s between them is den minus 1. We get the numerator for A by appending the end digit after n. In the first iteration, I is 0, so num does not have any 9 between 3 and 5. We divide num by den to evaluate A. We accept the value of A if it is not a fraction, so we find the remainder when num is divided by den. However, 35 is not divisible by 46, so we skip the if block statements and append a 9 at the end of n. It becomes 39 and numerator becomes 395. Even 395 is not divisible by 46. Its remainder is 27. It is clear that regardless of the number of 9s between 3 and 5, the numerator is never divisible by 46. Therefore, setting d equal to 1 won't yield a solution. After exhausting the loop over I, we finally proceed to the next value of d. When d is 2, then is 23. N starts with 3 once again. When I is 0, numerator is 35. It is not divisible by 23. Its remainder is 12. N becomes 39 for I equal to 1 and numerator becomes 395. Even this is not divisible by 10. For 395 divided by 23, remainder is 4. We attach another 9 to n and num becomes 3995. Even this number is not divisible by 23. When 39995 is divided by 23, the remainder is 21. If these remainders start repeating without first becoming 0, the problem has no solution. So, maximum number of iterations over I is 10, after which the repetitions of the remainder is inevitable. At that stage, we can conclude that a solution does not exist for the given value of d. This is the reason that maximum number of nines that we try in the solution is 10. Luckily, when we insert 20 nines between 3 and 5, the numerator for a is completely divisible by denominator. Unlike other programming languages, Python does not have a restriction on the length of integers, so Python is the most suited language for such problems. Remainder is 0 this time and the solution to the problem is found. Quotient of the division now becomes the value of a. In order to find the solution to the problem, we append the digit d at the end of a. To verify it, we multiply the solution by 5 by 4 and get the new number in which the digit at the units place of the old number is shifted to the beginning of the new number. Sometimes the first digit of a turns out to be 0, in which case the length of the old and new numbers is different. We have to discard such solutions. A related problem that we had considered is in which the new number is 3 by 2 times the original number. Old times factor is 3 and new times factor is 2. In this example, denom becomes 28 and n digit becomes 7. Loop over d shows that factorization of 28 gives d equal to 4 and den equal to 7. We now move to the evaluation of a for d equal to 4. Starting value of n is 1, for which num becomes 17. Its division by 7 gives 3 as remainder. For I equal to 1, n is 19 and num is 197. Remainder of 197 by 7 is 1, while for 1997 divided by 7, the remainder is 2. For 1997 divided by 7, the remainder is 5. For 199997 divided by 7, remainder is 0. This means that we have found the solution. We obtain a by dividing num by 10, that is 28571. We append d to this value of a and obtain the solution to the problem. To verify this value, we multiply the solution by 3 by 2 and get the new number in which digit at units place is shifted to the beginning, which ensures that our solution is correct. Further, the number of digits in the old and new are the same. In this session, we wrote Python program firstly to find the denominator of a by d and then iterate d from 1 to 9 to find digits that are factors of denom. The other factor of denom was used to find the value of a. In a loop over I, we increase number of nines one by one between first and the last digit till it becomes divisible by 10. AD becomes the solution to the problem. Further, we make sure that the number of digits remain unchanged when the solution is multiplied by 5 by 4. Hope you enjoyed the video. Please feel free to ask for further clarifications on my email address given below. I'm looking forward to your comments. Please stay tuned for more such videos.